Welcome to this special episode of Frequency Matters, the RF and Microwave Update Series. I'm Pat Hindle. I'm here with my new co-host, Del Pearson, and special guest, Tom Cole, Vice President of Sales and Marketing at Integra Technologies. Welcome back to the show, Tom.
Thanks, Pat. Always a pleasure to be back with the Microwave Journal team here on Frequency Matters, and we're really excited to share some updates on our high voltage GaN technology with you today.
Yeah, it's great that you come and check in every 6 months or so, and we'd like to get an update on the high voltage GaN process. You know, you've really positioned this as an innovative and disruptive technology. So how is it influencing the RF power amplifier market?
Yeah, we are excited watching literally weekly at new architectures that have emerged and very smart people doing amazing things when you give them a solution that is 600 to 800% higher than what they're using today. And so the power levels and the power density we've achieved has allowed us to do, I'll call it, transistors up to 8 kilowatts. Wow. Instead of just a 1 kilowatt device, which is the maximum you really could do at 50 volts. Mm-hmm. And so with that, on the solid state PA side, we have seen architectures transform. And so things that we have done in conjunction with our friends at Whirlitone on the power combiner side, with our technology in the high voltage GaN, the net result is we've allowed people to reduce their system size by 70% for the same power. And these are systems that are hundreds of kilowatts in power levels. It only gets better when you go up. So we're seeing really advanced architectures that we coined a term called swap C squared, because it's not just the size, weight, power, and cost, but it's the complexity. And that reduction of complexity by giving a higher transistor power has really enabled a system architect to come out and now radically reduce the size. So to give you an idea, a transition of a 150 kilowatt system was able to go from 2 6-foot high 19-inch racks to 1 4-foot high 19-inch rack. And by the way, we gave them from 150 kilowatts to 200 kilowatts power level. So 66% reduction in system size or volume and a 50 kilowatt sweetener in terms of the power level. So that is one aspect of the technology that we see with these very disruptive architectures taking hold. The other piece is really with the vacuum electron device or tube replacement. So that technology in some cases has become very difficult for customers to buy. And that's been a problem for ongoing concerns that have amplifiers designed with these large TWTs or klystrons. And so before high voltage GaN, you could replace a tube to about 10 kilowatts. That was practical. Anything above that, too much real estate, too many transistors, too many cats to herd in terms of phase matching, power combining, temperature compensation, and all the things you worry about at that level. So now, given transistors up to 8 kilowatts, those architectures become immensely simpler. And so what we're seeing is now the practicality goes from 10 kilowatts SSPA sizes at 50 volts. We've broken through that barrier, and now we are doing megawatt SSPAs with solid state. So we're actively engaged on 4 different programs that are 1 million watts or more per program. And again, these are to replace very large power tubes that they've lost their source of supply on. So it's been a really fun road watching these new architectures emerge and things that even beyond what we sought out to do and different markets coming in that we would have never planned for. But because the power levels have risen, and we always say we're providing system level powers in a component form factor, very smart people are doing really advanced architectures and reducing space, reducing cost, improving efficiency, and everything else that somebody cares about when you're designing a high power system.
And what are some of the latest market applications as well as kind of the future opportunities that you guys are looking at?
So I'll give you 3 that we've seen here very, very recently, including one that kind of came looking for us, which was always a fun way to find a new application for the technology. So one of the things, again, when we looked at the high power side of it, and we looked at certain applications for how do we change the architecture disruptively and give somebody a power level big enough to do something different. So a group that we've been working with now has a medical linear accelerator that they have created, and the medical linear accelerator treats cancer. So something that touches all of us through our lives. And what's really exciting and gratifying is that by going to solid state, we can help them to reduce the size of the system and to ultimately replace a magnetron that's driving this with something that would be much smaller. And this transforms a system that's on the order of this size down to something that's on the order of this size. And that's really, as we go through our kind of marketing and what we're looking to do, the premise that we thought is if we could give somebody a big enough power amplifier or transistor, they could radically reduce the system size. And so in this case, we've given them a high enough power level transistor that we can allow them to drive the linear accelerator with solid state. And there's a lot of benefits to that in terms of the pulse shaping and the ability to do different waveforms and things that you can't really do with a tube. So that's been one of the exciting ones. Another one is there are finding out an entire ecosystem of radioactive sources that are taken to different places to do inspections of critical infrastructure, nuclear reactor vessel walls, bridge structural members, all of these types of things that you can't do with an X-ray because you can't generate a high enough energetic beam to image microcracking in those members. You can do that with a linear accelerator. And so with that, think of the obvious dangers of having radioactive sources all over the world that are checked in and out and have to be controlled and maintained and monitored for obvious reasons. Now you can replace that with solid state. And so this would be something that from a safety concern and that we can now see, again, a path to that technology proliferating. There are several companies already working on this and have been for some time. And it's exciting to see in the progress they've made when we're able to give them a 6, a 7, and 8 kilowatt device where they can now architect something much smaller and much safer. So we're very excited for that one. And then in our more traditional space, we've even seen the UHF radar. There is a resurgence for a particular type of airborne radar that has a substantially higher ability to detect certain types of aircraft. So from a safety of service members and other people that are deployed, this is a really exciting one because we've gotten them now to they used to have to combine multiple devices and pay an efficiency hit for each of those power combinations. Now we've given them a single device per element. So that saves weight, it saves aircraft efficiency through not having to burn that energy in terms of heat loss. So all of that is found efficiency and found fuel mileage for the aircraft generator. So really exciting things that we're seeing architecturally, all brought about again by the power levels that high voltage GaN can produce.
Those are very interesting examples. I love them. And so looking to next generation systems, what is the next step in the evolution of Integra Technologies?
So as we've brought these power levels up to system level powers in these small form factors, it has lent itself to the drive for AI and the ability to have machine learning influence or adapt and control a given type of power amplifier waveform. So what we have done and what we are now working with a European prime on and have released a digital palette platform. So this would be a high voltage GaN RF section with a multi-block RF or digital to RF block around it, where you can do things like temperature compensation, you can do power monitoring, you can do dynamic waveform adjustment, all things that our end customer has to be able to do with this. And now we've given them the ability for the command, the control, the monitoring on this RF amplifier palette to be done digitally. And so that is a really exciting advancement where we're driving this in the direction, if you think about a server blade, right? You have a different blade card that you insert for additional processing power. Same thing would apply to RF. We have these modular RF amplifiers that are the digital palette form factor, and you can combine them. So you can put 100 of these things in at 10 kilowatts each to make very, very large SSPAs and have them with the nicety of being able to digitally control them, to be able to use AI to, let's say it's a directed energy system, radar resolves a target, you determine what the waveform that's most effective to defend against that, you change the waveform, maybe you take the PA, you go up 20 volts, and you go ahead and send out that waveform that affects the target and defends against it. And then maybe it's another target that has a different waveform. You can dynamically adjust that, optimize the voltage, the pulse width, the duty cycle, and now you can affect a different type of target on the fly. So that's where we see the architectures going, whether it's radar, directed energy, or even on the medical and industrial and particle accelerator sizes, where you would want to be able to dynamically control those amplifiers to do different functions that the end item requires. So pretty exciting things, and we look forward to watching that evolution here as we continue to bring the power levels up through the high voltage GaN technology that we've been investing in for a long time.
Awesome. That's very exciting. And we hear you have some more exciting news regarding your channels to market. Can you share that?
We do. And this one, particularly exciting to announce that in March, we signed an agreement with Richardson RFPD. And so they are a premier RF and microwave, not only distributor, but I really look at them as a business development extension arm for Integra. They have a number of sales engineers and a number of field applications engineers who live and breathe RF and have done so for many, many years. And I've had the pleasure of working with them in previous companies and in different capacities. So we're really excited about the partnership and the reach that brings. So we looked at this, and between the Richardson RFPD team and Integra, the scale that Richardson brings and the focus, and having had so much industry breadth of doing RF and microwave for many years, combined with a very unique technology in the high voltage GaN, was the perfect intersection to bring the two companies together and work together. So we're excited for the partnership, and I'm even excited for the extensive travel that I've promised to do with them. But it's for really exciting reasons, and we look forward to expanding the reach for Integra and really engaging with the RFPD team as time goes on.
Awesome. Thank you, Tom. That wraps up our episode. And thank you again for spending some of that extensive travel to come and be on this episode. We appreciate it.
Well, thank you guys for having me as always. It's always a pleasure, and we look forward to doing these in the future and keeping you all apprised of what we're doing with high voltage GaN.
Fabulous. To our viewers, you can find more videos at videos.microwavejournal.com, and thank you for watching.